Okay, so hi everyone, my name is Miroslav, I'm from BUT, from Brno, and I would like to describe you what we have done for this year Zero Cost Speech Recognition Challenge. This year the task was a little bit different than in previous years, but we had some previous knowledge of low resource languages. And also we have some other systems trained we used on MediaEval project, which focuses on low and also in rich resource languages. So we take this and we try to adapt that on this year's target language, which was Vietnamese. We also have to follow zero cost requirements, which means everything we used have to be for free. So at the end we ended up with some data processing and cleaning. We had 2 ASR systems and 1 subword system. We also find some interesting ideas for some further improvements. So at first we focused on some cleaning on the data. With the audio, we only downsampled the original 16 kHz audio to 8 kHz because one of our systems works with 8 kHz audio. That's all for audio, and now we had some transcriptions. So at first we took the provided word list with 70,000 words, and we extracted some set of valid characters from Vietnamese alphabet, and we use this to filter out everything else. For example, brackets, parentheses, and everything else. We also focus on numbers, because some numbers were in the numeral or they were in a digital form. So what we did, we took the translation of the basic Vietnamese numbers, and because Vietnamese build their numbers by very simple rules and in a very logical way, we could translate the numeral form to the textual form, so we can keep the numbers. So the other thing is segmentation. This part is not that important because it does not improve the performance of the system, but it helped us to find out some interesting ideas for further processing, like detecting wrong or broken transcriptions or transcriptions that are not fitting the audio. So what we did here, that we took the alignment from the early stages of training and we used it to detect silences. Every time we detect silence which is longer than half a second, we split the segment here, so we don't have any problems with high memory demands of while training. We did the same with the segments longer than 15 seconds. We split it at the very first silence detected. The next thing is that we ended up with 3 language models. The first experiments were done with only with the language model trained on the clean transcriptions. The other language model we got from the subtitles. We also cleaned that in the same way. And the last one was that we got provided a list of websites, so we downloaded the content and also cleaned it in the same way. We filter out lines with less than 3 words because we were training 3 states language models. And at the end we combine them together in a linear way using the development set as for tuning. So here is some simplified diagram of our first system. This system is a little bit worse than the second one. This takes 8 kHz audio and the cleaned transcriptions. Again, briefly describe what we did there. So we take critical band energies, and also, as mentioned, Vietnamese is a tonal language, so the fundamental frequency F0 were also important for us. We stack together, we send it to stack bottleneck, which is on the top picture. These are two similar DNNs. When you put the features as the input for the first network, and you take the output from the bottleneck and stacked 5 following vectors on each other and downsample, and you put this on the input of the second network, so this follows some context in the speech. So the lower branch, there are PLPs, there is some normalization, capsular mean and variance normalization, and to reduce dimensionality there's HLDA. We stacked again these features and put it on the region dependent transformation, which is a set of transformation according where the input feature fits. This is trained to follow minimum phone error. There's another adaptation CMMLR, and at the end there is GMM decoder. So this is our first system. The second one is similar to the first one, but there are some differences. The lower branch, there are no PLPs, but there are MFCCs. Again, there are 2 transformation, speaker adaptive transformation and MLLT. And here at the end, there is the third DNN, because the 2 are still there in the stack bottleneck part. And at the end, there is bidirectional long short-term memory. What happened there that you have the alignment from the GMM decoder, you put it on the VLSTM, and you have some improvement on the alignment. There are 2 iterations, so you take the alignment and put it again as the input for VLSTM. This system takes 16 kHz audio, and what's interesting that we don't use any cleaning, we used original transcriptions in here. The whole system is in Calvi, except the last part, the VLSTM is in TNet toolkits, but these toolkits are compatible, so it's not a problem to combine these. For our second subtask, the server system, we used acoustic unit discovery model. So in here task you don't need transcription, you are working only with audio. It works like phone model, but there are no HMM, it's fully binomial. So there is no need for fixed numbers of HMM. At the beginning of training it starts with infinite number and it learns the complexity. So here are some results. You can see that we beat both the baseline system for both tasks. Our best ASR is VLSTM with tuned combined language models, and for the solver task you can see that our system works a little bit better than the baseline. What's interesting is that our worst system, ASR system, the GMM DNN, has worse results, but for the unseen data, which was the YouTube data set, there we got the best results from all our systems. So some ideas for future experiments. It would be nice to find some better way how to clean transcriptions, because there always will be some inserted words or missing words in transcriptions. We can use the alignment from some further stages during training to do some analysis and to find out some strange behavior, like too long phonemes or too long silence. And of course, to make the system more robust, we can take the input audio and add some noise, and the same goes for reverberation. So I think that's all from me. Thank you for listening.